analysis of algorithms, asymptotic notations. During this session, we shall work out a few problems and find out the complexity of some of these algorithms. Here you have the first problem. Find the complexity of recurrence given below. So here you have a recursion formula. T to the n function, this Tn is equal to T 3t into n minus 1 if n is equal to greater than 0. If t 0, if n is equal to 0, it is going to be 1 otherwise. So this is the recursion formula. What we'll have to do is we'll have to expand this recursion formula and then get the answer. So we write therefore Tn is equal to 3 into t to the power n minus 1. What is the expansion of Tn minus 1? Again, you plug it into this. It becomes therefore 3 into 3t into n minus 2. That is n minus 1 minus 1 minus 2. Similarly, then it becomes 3 to the power 2 into Tn minus 2. What is Tn minus 2? Again, it becomes 3t into n minus 3. Therefore, t to 3 to the power 3 into n minus 3. So this way you go on. And then at one point it becomes the 3, it becomes, this integer becomes n. So it becomes 3 to the power n to t to the power t0. T0 you know is equal to 1. Therefore 3 to the power n into t0, that is equal to 3 to the power n. So we have the answer for this problem. Therefore complexity of this recurrence formula is nothing but big O of 3 to the power n, 3 to the power n exponential equation. Okay, with that we come to problem 2. A similar problem, find the complexity of the recurrence. Tn is equal to 2 into Tn minus 1 here for if n is greater than 0. If it is 0, it is 1. Let us see. Again, we do the expansion. Tn is equal to 2t of n minus 1 minus 1. Now we have to substitute therefore 2, that is Tn minus 1. It becomes therefore t into n minus 2 minus 1. As you see, within brackets, therefore this one t2 into Tn minus 2 minus 1. So what does it become? Therefore 2 to the power 2 Tn minus 2. So minus 2 it becomes, because you multiply by minus 1 by 2, it becomes minus 2. Again, this becomes therefore t of n minus 2 becomes 2t into n minus 3 minus 1. So that is an expansion, 2 to the power 3 to tn minus 3 minus 2 to the power 2, 2 to the minus 1, etc. So just have a look. 3, this becomes 2, 1, etc. So if you go on expanding, it will come to one position. Therefore, 2 to the power n is equal to 2t n minus n. So if it is 3, it is 2. Therefore, 2 to the power n minus 1, n minus 2, etc. going up to 2 to the power 0. 2 to the power 0 is equal to 1. So we'll again, so that becomes therefore 2 to the power n into t0. Therefore, it is 1. Then minus t to the power n minus 1, etc. going up to 2 to the power 0. That is equal to 2 to the power n minus 2 to the power n minus 1. The summation of this is just 2 to the power n minus 1. We have done that when we did the algorithms. So as you see it here, so 1, that is 1 plus 2 to the power 2, 3, etc. is equal to 2 to the power 4 minus 1. You remember in when we did the tree, so h plus 1 minus 1. So that is the formula we are using here. So you can simply check it and see. So therefore this becomes 2 to the power n minus 2 to the power n minus 1. So simplify, this cancels and therefore it is 1. Very simple, though the formula looked complicated. We see that the complexity of algorithm is of the order 1. Order 1 is the best algorithm or best complexity of the order 1. With that, we come to some functions now and find out the complexity of this function here. So function says if n is equal to 1, return. Otherwise, for n is equal, I is equal to 1 to n, here also within one more here, I is equal to j is equal to again up to n, j plus plus. You print this, but there is a break here, You just check this. What could be the complexity of this algorithm? We'll work on that. So we take the solution. So solution is, since the inner loop here, So this is two inner loop. There is a break is here. Therefore, once it does, every time it breaks, every time it sprints and breaks, it doesn't go forward. Therefore, it will only run from 1 to n, just 1 to n. Therefore, the complexity of the algorithm is of the big O of n. That's because of the first loop. From 1 to n, every time this breaks. Suppose there was no break statement, it would have been n square. So n square, please remember that. Come to problem 4. Find the complexity of the function below. So void function n. Again, count is equal to 0. For I is equal to n by 2 going up to n I plus plus. For j is equal to n, j is equal to less than equal to n. And here you have to, so it goes, jumps by 2, like the binary tree jumps by 2. So, and here again, it jumps by 2. For k is equal to 1, k is less than 2, jumps by 2. K value jumps by 2, 4, 6, 2, 4, 8, etc. 16 it will become. So, count plus. So, what is the complexity of the algorithm? So, we have to take each of these looping statements and find their complexity. So, let us check for first one. So, I is equal to n by 2 to n, therefore, is half the number. It is going to be n by executes n by 2 times. So we have to find out how many times these looping statements execute. Then we come to this problem. Here, as you see, it is 1 to n, but it is jumping by 2, 2, 2, 2, 2, 4, 8, etc. Therefore, it is like the binary tree. It is going to be of log n, log n. When it is jumping by 2, it is going to be log n n to the base 2, please remember. Then again we are coming here, it's almost the same, k is equal to k into 2, it is also log n. Therefore, what is the total complexity? So these are one inside the other, not one, they are separate loops. If they are separate loops, it would have been plus plus plus. So here, since they are one inside the other, so to multiply, therefore, n by 2, then log n by 2 is equal to n. Therefore, time complexity is going to n into log n into log n. So that is in other words, it is of the order n log squared n, n log squared n. With that, we come to problem number 5. Find the complexity of the function here. Again, you check here. It is from n by 2 to n. So here it is j is equal to 1. So j plus n by 2 to n, again by n by 2. So here it is 1 to n, but it is jumps by 2. Therefore, it is going to be log 2. So let us check that. So first one is going to be n by 2 times. Second also going to be n by 2 times. Third one is going to be of the log n times. So multiply these three. Therefore, you get n by 2 into n by 2 into log n. Therefore, the complexity is of the order of n squared log n, n squared log n. We take one more example. Find the complexity of the function given below. So how much time, asymptotic time it is going to take. So that is what you have to do. Just check the formula here. So as long s is less 1, as long as the value of s is less than equal to n. So n is given here, n may be 5, n may be 10. So you have to go on finding it. So what does this formula do? I plus plus, it is adding 1. So it is adding s is equal to s plus I. It is going to find the sum of numbers, as you see. It's going to find the num up to k. So 1, 2, 3 up to k it is going to find. So it goes on finding. And so of course up to n it is going to do. So what is the sum of these? You know the formula. It is a sum of natural numbers. The formula is given by k into k plus 1 divided by 2. So this is the formula. Now in other words, the s has to, as long as s is below n, less than equal to n, therefore we will equate it. So since s is less than equal to n, so therefore the value of this formula should be less than equal to n, or as you see here, it is going to be k squared plus k divided by 2, etc. Or k is, so you simplify it, because we leave that k form, k squared is there. So k is less than equal to power square root of n. So k is square root of n. So that is going to be therefore the complexity of this algorithm of the order of square root of n, square root of n. Thank you.